So I'm trying to copy these two important lemmas here. Recall. Oops. So last time, the two important lemma we've seen is this embedding lemma and counting lemma. Let me quickly go through what they are talking about and see one more application of it. Okay. Good. So, lecture 25. So regularity lemma once again saying that for any graph we given, we can find the partition of its vertex sets, an equipartition into bounded number of parts such that almost all paired of parts, apart from an epsilon fraction, they behave pseudo-randomly. Pseudo-random as in this definition of being a regular pair. And the nice thing about between a regular pair is we see some nice property of it. For example, the vertices most of the vertices, the typical vertices, they have the correct degree to the other side of the pair. The embedding lemma, one of the key lemma associated to regularity lemma, is saying that, so recall the definition of the reduced graph. Reduced graph, basically, when you have these clusters from the partition of G, you shrink the clusters down to a single vertex. You put an edge between two corresponding clusters in the reduced graph, if only if it's regular and dense. And this graph R, the regularity lemma and counting lemma is basically saying that this reduced graph R preserve this the information, essential information of G in terms of the subgraph density. So here it's saying that if we have a graph with maximum degree delta, then as long as each part of the regular partition is sufficiently large, larger than this S is the key one, larger than after this is constant. Okay, 2 is a constant. D is a constant, which is the density, lower bound on the density of each regular pair in our reduced graph. Delta might not be a constant. Okay, so we have delta here. So you have this number and S. So what it's saying is that if there is a homomorphism from H to R, in other words, if H is contained in the blow-up of R, then H is contained in the original graph G. And here, if the graph H you want to embed has bounded degree, this is the important remark. So if delta is bounded, then we can have the order of H to be linear in the order of G. We can embed a really large graph, linear in the size of the host graph. And in this proof of embedding lemma, we see that the way we embed a copy of H, there's lots of room. So we can get the counting version saying that not only we have a copy of H, we have many, many copies that's proportional to the count in the weighted graph R. So here's like a baby simple example. If this is our reduced graph on 3 vertices, a triangle, and let's say the density between the pairs is 1/3, 1/2, 1/4. Then the weighted count of triangle in this reduced graph is nothing but just a single triangle here. And you have to multiply by the weight of this triangle, which is the product of the weight of the edges. It's 1/24. So then the corresponding graph here, the number of triangles with one vertex in each part is the same proportion. That's basically counting lemma, which works for more general graphs than just triangles. Okay, so now last time we see the application in Ramsey-Turan theory. Today, let's see an application in Ramsey theory to appreciate that, to see also that why partition G into a bounding number of parts is important, because that can guarantee, together with the fact that maximum degree is bounded case, the graph we want to embed, then we can embed something up to linear size of the graph. This application is a result in Ramsey theory, the Hvatal-Rödl-Semerdy-Trotter theorem, which is basically saying, unlike the complete graph we've seen, whose Ramsey number is exponential in the order of the complete graph, for graphs of bounded degree, the Ramsey number is linear. So let's recall. This is Hvatal Rödl Semerdy Trotter. This is an application of regularity lemma and embedding lemma in Ramsey's theory. So let's recall. Given the graph G, okay, given the graph G, its Ramsey number is the minimal integer n, such that any 2-edge coloring, for any 2-edge coloring, of the complete graph on capital N vertices, we can must contain the monochromatic copy of G. Monochromatic copy of G. Okay, and recall the Ramsey number for cliques KT, it's exponential in the order of the graph. So KT is less than, now it's something slightly less than 4. Let me write it like this, and bigger than roughly square root 2 to the t. So you can write it as, this should be t. Let me square root 2 to the t, so something like 2 to the t over 2. Now we will see a very different behavior of the Ramsey number, also on t vertices, but not exponential. This is exponential in t. But clique, it's very dense. We consider a very sparse graph. In particular, we consider graph G that has bounded degree. So this is CRSZ, abbreviated as CRSZT. TR. So CRSZ TR is saying that for bounded degree graph G, Ramsey number is linear instead of exponential in the order of the graph G. Here's the theorem. Let D be a natural number, which will be the maximum of degree of our graph G, and G be a graph with maximum degree D. Conclusion is the Ramsey number of G is linear in the order of the graph G, where this constant of course depends on maximum degree D. So think of this as a constant, whereas let's say if n is the order of G goes to infinity, so for this result, we're going to use a small variation of the regularity lemma, which is the multicolor version of regularity lemma. It's basically the same. Before I state it formally, regularity lemma is saying if you have a graph G, I can partition its vertex into bounded number parts so that between most of the pair, it's regular. You can look at the edges there. But now, in the multicolor version, the graph comes with some edge coloring. So for example, in our Ramsey problem case, you have a complete graph. We are coloring we have a complete graph coming with a two-edge coloring. But in the multicolor regularity lemma, it doesn't have to be two-edge coloring. Any bounded number of colors, you have a graph with whose edges are colored by bounded number of colors. We can find a partition of these vertex sets such that between most of the pairs, if you look at any color, it's regular. Multicolor regularity lemma. So we have to define what's the epsilon regular partition for a K, let's say colored by K colors, K edge colored graph G, a partition V of G is an epsilon regular partition if, so here I just throw away the exceptional sets, assume that there's no exceptional set V0, but instead Vi, every V1 to Vr, their size might not be the same. They could differ by up to 1. So for all ij, all pairs, their size differ by m-most 1. And most of pairs are regular. for all but epsilon r square pairs the pair VI-VJ is epsilon regular in every color. When you look at the VI-VJ, now it's not just a graph anymore. You have graphs with edges in K colors. So if you look at a single color, look at the corresponding graph there in this color, it's regular. So this is important in every color. And the one we need is just K equal to 2 here for us, for 2H coloring of the complete graph. So here's the multicolor regularity lemma. For every real epsilon between 0 and 1, and every integer k and m, there exists a capital M, which is a constant, depends only on epsilon, m, and k, to upper bounds the number of parts in the reduce in the regular partition, such that every kh colored graph G with n, which is at least m vertices, admits an epsilon regular partition into MR parts with, so what's important here is that number of parts is bounded by these two M's. Now you can define reduced graph in the same way. Then we can similarly define a reduced graph corresponding to a regular partition with the only difference so before we put an edge between two corresponding clusters in the reduced graph, if and only if it's regular and dense. Here, between the pair, there are k graphs in each color. So we put an edge between two clusters in the reduced graph, if and only if it's regular with respect to every color. If and only if VI-VJ is regular with respect to every color. So here, for this application's purpose, We don't care whether the pairs is dense or not, because there's k-graphs between a pair, Vi, Vj. By pigeonhole, okay, no. We need all edges to be there to use pigeonholes. In our case, we do have all edges because it's considered a complete graph. So let's not mention about density for now in the reduced graph. We put an edge between ij in the reduced graph for the multicolored case, if and only if Vi, Vj is regular with respect to every color. We don't care about their density. Good. So now we can use this to prove these Ramsey results. To do that, let's recall one more tool we need, a very basic one in intro class of graph theory, the Brooks theorem. Brooks theorem is saying that if you have a graph with bounded maximum degree, with maximum degree d, then we can give it a proper vertex coloring with d+1 colors. For every graph G, can be properly vertex colored using maximum degree +1 colors, i.e. chromatic number of G is at most delta of G +1. Equality holds for when G is a clique or odd cycle, for example. The proof is very simple for this Brooks theorem. Just greedily color things. For every vertex, and most delta colors are used in its neighborhood. So at least one color is mixing. When we have this many colors, you just use one of the mixing colors to color the vertex. You can greedily finish the coloring. We need these because remember, recall, we want to embed the graph with bounding maximum degree. And one of the things we need is that there is a homomorphic image of this graph in our reduced graph. When your graph is delta +1 colorable, then one of your homomorphic image is just the clique on delta +1 colors. Okay. So let me first write down the idea, and then we're gonna see the rigorous proof. Idea of the Hovato Rödel Semerity Trotter. So because G, we have K delta, recall our graph G. Here's the statement. We have maximum degree D here. So KD +1 is a homomorphic image of G. AD plus 1 is a homomorphic image. To find the monochromatic copy of G, this means by embedding lemma, finding monochromatic copy of G is the same as it's enough to find a monochromatic KD plus 1 in the reduced graph. R. Okay. Heuristically. So all we need to make rigorous is, what do you mean by monochromatic copy of KD plus 1 in the reduced graph? We did define the reduced graph in the multicolor regularity lemma, where an edge represents a pair of cluster that's regular in every color. We didn't give a coloring on this reduced graph. In this case, we're going to use the majority coloring. So when there is an edge in the reduced graph, we know that VIVJ is regular for every color. Now we can give it a coloring. We can color IJ by the majority color, meaning whichever color has the most number of edges between VIVJ. Here, we will color the edges of the reduced graph by majority coloring. The majority color. Okay. And very simple, look, we have VIVJ. If in the reduced graph, R, there's an edge between IJ, then in our complete graph, Kn, so what do we need to prove? We need to prove that there is a capital N that's linear in the order of the graph G, such that when you give a two-edge coloring of it, we can find a monochromatic copy of G. So in Kn, the corresponding VIVJ in the multicolor regular partition, you will see two kinds of edges, red or blue. And you have all edges between them. So density is 1. And since there are two colors, one of the color will have density at least 1/2. So in majority coloring, this implies by pigeonhole every if IJ is in color red, then VIVJ has red density at least 1/K. Okay. When you have K edge coloring. Good. Now we can start our proof. So you start with a complete graph, apply regularity lemma, you get a reduced graph, coming with a majority color. So so that means between every pair, the corresponding color has density at least 1/2, k equal to 2 here. Good. How do we use embedding lemma? We need to find a monochromatic copy of a clique kt plus 1 in R, which is a homomorphic image of G. How do we do that? Well, because most of the pairs, they are regular in every color. So in the reduced graph, we have almost all edges presented there, apart from epsilon fraction missing. You can then use Turan's theorem to find a large clique in R, then apply Ramsey on this large clique to find a monochromatic kt plus 1, and then apply embedding lemma. Done. Let's write this down. So first, let's set up some parameters. Let M to be the number of parts in the regular partition, a lower bound on the number of parts, to be at least, let's say, some constant 5 times the Ramsey number of kd plus 1, kd plus 1. Okay, so this is the number such that when 2H color the complete graph, you'll get a monochromatic copy of kt plus 1. So you let M to be this, and epsilon is 1 over M. And I think to be precise, the order should be we first take epsilon, and then we take M to be bigger than the maximal. Wait, let me write it more rigorous. The maximum of this and 1 over epsilon. Okay. And we're going to take a constant C to be, this will give us, by regularity lemma, multicolor one, a capital M that depends only on epsilon M, and we have a 2H coloring, right? This is the one from regularity lemma. After we get this upper bound on the number of parts, capital M, we define constant C to be 2 times this capital M over 1/2 minus epsilon to the power D. These are the constant setting. Now we're going to let capital N to be at least this constant C times G. Remember what we need to do? We need to prove that Ramsey number of G is linear in G. So this number is linear in G because C is an absolute constant, depending essentially only on this D and epsilon we're choosing. So now we just need to prove when you 2H color Kn. So first, fix an 2H coloring. Fix an arbitrary 2H coloring of Kn. What we need to do, we need to find a monochromatic copy of G in this coloring. Which then would imply that the Ramsey number is at most capital N. This will imply the Ramsey number of G is at most C times G, as we want. So we're going to apply multicolor regularity lemma to this two edge colored Kn. Yeah. We apply a regularity lemma, then we get the reduced graph R. R is the reduced graph with majority coloring. Okay. Now, first thing, if we forget about the colors on the edges of R, just count the number of edges of R. How many edges in R? So, because as a most epsilon fraction, is this easier? So let me actually change to epsilon fraction instead of epsilon R square. This doesn't matter. Just normalization differently. So because there are at most epsilon fraction of the pairs are irregular. By irregular, I mean irregular with respect to some color. This implies that the number of edges in R is at least, apart from epsilon fraction, all the other pairs, they are regular with respect to all colors. Now this, by our choice of epsilon, one second. What I want to say is this is bigger than 1 minus 1 over m over 3 minus 1. Choose or choose 2. Okay. Let me see why this is true. We just need to compare epsilon and this guy, right? So this is bigger than this, basically. Or this is bigger than epsilon. Yeah, that's true. Because, oh, I see. So I really mean, because here we need this, which is the same as 3 over epsilon bigger than m. So we really want m to be not much bigger than 1 over epsilon. So I was right at the beginning. Sorry. So you really set m to be this Ramsey number. And then you set your epsilon to be 1 over m. In this case, we do have this inequality here. Now by Turan's theorem, we get that R contains a copy of K m over 3, the complete graph on m over 3 vertices. But what is m? M is larger than 5 times the Ramsey number. So m over 3 is still bigger than the Ramsey number for KD plus 1. If you now zoom into this clique on m over 3 vertices in R, now we have the colors back, the majority color comes with the red and blue coloring. Apply Ramsey. By Ramsey, by definition of M and Ramsey, we get that R contains a monochromatic copy of KD plus 1. Okay. Now at the end, Brooks' theorem implied that KD plus 1 is a homomorphic image of G. Then embedding lemma at the end, that's it. So it's important that the number of parts here is upper bounded by some absolute constants. So even when you zoom in, when you have the reduced graph, even if you zoom in the subparts of the reduced graph, here we zoom twice, right? You first use 2run on this almost complete reduced graph R. You zoom into a clique. Now you have the colors come into play. You use Ramsey to zoom into a monochromatic clique. We lost a lot of information of the graph G. We zoom into some part of R. But since the total number of parts is constant, this monochromatic KD plus 1, if you look at all the vertices in the original graph corresponding to this, is still linear in this host graph, capital N. Any questions? Now we're going to move on to another lemma, which is equally important, as important as counting lemma and embedding lemma. The triangle, the removal lemma. Let's talk about Ruja Samarides triangle removal lemma. Informally, what he says is the following. Informally, it's saying some very intuitive thing that for any graph, almost triangle-free graphs. By almost triangle-free, it just means the triangle density is 0. The triangle density is 0. In other words, there are little o. So when you have positive fractional triangles, how many would there be? There are n to 3 possible triples. If 0 density, that means little o of them, little o of n cubed form a triangle. So little o n cubed triangles. That's what we mean by almost triangle free. We can destroy all triangle of it, make it triangle free by removing a negligible amount of edges. And here, what do you mean? The negligible amount? The number of pairs of edges, all possible pairs, n choose 2. Negligible means little o of n squared edges to remove. This is what it says. Very intuitive. Let's write down the formal one with the quantitative constants. Lemma. This is the removal lemma from 1976. So given constant c bigger than 0, there exists the constant a depends on c such that the following holds. For such that for every sufficiently large n, the following holds. Let G be an n vertex graph if G has at most an cubed triangles, then it can be made triangle free by removing at most cn square edges. Okay. It's also instructive to see the contrapositive of these statements. So what is the contrapositive statement? You negate the conclusion, implies that you can negate the hypothesis. So if you have a graph that cannot be made triangle free by removing little o n square edges, then this graph must have lots of triangles, meaning it has a cubic number of triangles, positive triangle density. What does it mean a graph cannot be made triangle free by removing few edges? That means this graph has many edge destroying triangles, right? If you have many edge destroying triangles, in a large collection of edge destroying triangles, you have to remove an edge from every triangle in this collection to destroy them. That's the contrapositive. Let's write it down. So contrapositive is saying if one cannot destroy all triangles by removing few edges. And what this means is that there are many edge disjoint triangles. Then the graph contains a positive fraction of triangles. Many triangles. We will see some application of removal lemma, but first let's prove this lemma today. To prove this, it's good to introduce, I would say very standard nowadays, a procedure, which is a cleaning process for a graph when we apply regularity lemma to it. So let's consider a cleaning process. So cleaning the graph G, it is convenient to define a subgraph, let's call it GR of G, corresponding to a reduced graph. And by cleaning, obtained by keeping only edges between regular and dense pairs VI, Vj, for which we have an edge in the reduced graph. This is a very standard thing. Remember, we passed from a partition to the reduced graph. And in the reduced graph, we only keep edges that are regular and dense. This is basically saying that you just delete those edges, the information of G that's not stored, that's not represented by R. And this amount of edges that we delete is negligible. So let's see. So the following cleaning process is standard. And the edges deleted that means the edges that's not kept in GR is the non-essential information we discard when forming the reduced graph. Okay, so here's the cleaning process. We will actually show that the number of edges we cleaned, so GR is the subgraph we keep. The number of edges is almost the same as the number of edges in G minus little o n squared. So you only clean out negligible amount of edges. The edges that we clean, there are three types. First, we remove inner edges. This means edges in VI for every part V1 to VR. Let's suppose V0 is empty. Each VI differ by size at most one. Since we choose by choosing M at least 1 over epsilon when applying regularity lemma, we know that the number of edges inside each part is negligible. So that the number of parts is at least m, which is at least 1 over epsilon. We know that number of such edges is at most. Each part is roughly n over r size, vi. The number of edges inside each vi is at most. The worst case, you have everything there, times you have r parts. So altogether, this is less than n squared over 2r, which is less than n squared over 2m, which is less than 1/2 epsilon n squared. Next, we're going to delete. So we only keep dense and regular. Now we need to delete all those that's either not dense or not regular. So let's look at those that are not regular. Remove edges between irregular pairs. The number of irregular pair is at most epsilon r squared, implies the number of such edges is at most. So between the regular pair, the worst case you can have, you have all edges there between n over r, n over r. This is again, this equals to epsilon n squared. The remaining kind is the sparse one. That means density less than delta. Remember, in the reduced graph, we define an edge when it's epsilon regular and density at least delta. So the number of such edges is at most. Between the dense pair, the most number of edges you can have is delta times n over r squared. And the total number of pairs is at most all possible pairs, r choose 2 of clusters. This is at most 1/2 delta n squared, very small. So all in all, total number of edges deleted is at most 1/2 n squared times 3 epsilon plus delta. Just some linear in epsilon and delta times n squared. And usually we're going to take epsilon and delta to be sufficiently small. So this is little over n squared. All right. I will write this process once. In the future, I will just refer this as the cleaning process. We will not do this again. Now let's prove removal lemma. Let's first see the idea. Idea for proving the removal lemma. The idea is simple. We're gonna prove it by, so you have G that's almost triangle free. right? That's what we're given. And we need to show that we can remove little o n square edges from G to make it actually triangle free. And the one we're going to remove is basically just the edges not lying in GR. So first of all, we notice that G being almost triangle free actually implies the corresponding reduced graph is genuinely triangle free. Must be triangle free. Why the reduced graph must be triangle free? If you ever see a triangle in the reduced graph, then by counting lemma, it will correspond to a positive fraction of triples in G forming a triangle. Or otherwise, counting lemma implies there are positive fraction of triangles in G, which is a contradiction to G being almost triangle free. Good. Now if R is triangle free, we are done. GR, this cleaning process we just explained, delete little o n square edges, then GR must be triangle free. Then, thus, G can be made triangle free by removing few edges not corresponding to R, i.e., we're going to go from G to GR. That's how we remove things. Another remark here is that another way to see this last line is by removing all those edges not corresponding to R, GR is a random blow up of R. It's a random subgraph of blow up of R. But since R is triangle free, its blow up must also be triangle free. So is its random subgraph. So GR is triangle free. That's another way to look at it. So now let's write this proof more rigorously. So we're gonna prove we're gonna essentially prove the contrapositive, right? So let's suppose it's not true. Suppose not true. What does it mean? That means, this means there exists a C bigger than 0 such that for any A bigger than 0, there is a counterexample. There is a graph G such that it satisfies two things: the number of triangles in G is at most an cubed, and the removal of any Cn square edges does not make it triangle free. This is the opposite of the conclusion we want to prove. Suppose this is the case, we're going to derive a contradiction. Well, we have this C now, we we have this C now, such that for every A, we can find this graph G. So let's determine A later. With A to be determined, let's grab this counterexample G, satisfying that it has few triangles, but very hard to make it triangle-free. Apply regularity lemma to G. With an epsilon that's much less than C, and we're going to take M to be 1 over epsilon. This will give us a regular partition. This regular partition will give us a reduced graph. We're going to take reduced graph. R equal to epsilon C over 4, meaning you put an edge between the pair of clusters when it's epsilon regular and density is at least C over 4. Now we're going to consider, when you have R, we can consider the clean graph GR. GR in G, as we did above. What do we know? We know that in this process, the number of edges cleaned is n squared over 2 times this 3 epsilon plus delta. So it's n squared over 2, 3 epsilon plus a delta. Delta is this guy. But C is much bigger than epsilon. So total number of edges we deleted is at most C squared over this. Imply that the number of edges deleted is at most C n squared over 2 by the previous calculation. We don't delete too many edges. What do we know about GR? Since we didn't delete many edges, by our hypothesis, no matter how many edges, no matter what set of Cn squared edges we delete, we cannot make it triangle-free. That implies that our graph GR must contain the triangle. By hypothesis, by assumption, by the choice of G, GR contains a triangle. But where can this triangle be? Since GR is a blow-up of R, this triangle must have each of its vertex in 3 different parts of the partition of G, such that between every pair it's regular and dense. And by construction of GR, this triangle in R, any a triangle, not this triangle, we know it contains a triangle. A triangle in GR, where can it be? A triangle in GR must have its 3 vertices lying in 3 distinct parts or clusters, say Vi, Vj, Vk, such that are pairwise regular and C over 4 dense. Okay, so we have every triangle in R must lie in some triple that are pairwise regular and dense. Good. So all this density is C over 4. We can use counting lemma on this triple of clusters. By counting lemma, it implies that the number of triangles in GR between VI, VJ, VK is at least, what's the number? If you recall, the counting lemma is saying you have the density raised to power 3, and each part of this VI has size n over R. You need to minus some constant times the regularity epsilon. So let me just put big O epsilon here. Since we choose C to be much larger than epsilon, so big O epsilon is still much smaller than C. I've been a little bit not so precise here. You can make it rigorous. So we still have at least say C over 8 inside here, raised to power 3 times this, blah, blah, blah. This is at least C over 8 R cube n cube. But R is at most, remember R is at most capital M in this regularity lemma. So we have this is at least C over 8M, but M is a constant of what? M is a constant of epsilon and little m. Little m, it depends only on epsilon. So m depends also only on epsilon. So this depends only on epsilon. C, much bigger than epsilon, essentially depends on epsilon. So everything is about epsilon. You have these times n cube triangles. But m depends basically only on epsilon, hence only on C. We just need epsilon to be much smaller than C. So this is a function of C. We can choose A as a function of C to be less than this thing. So we have, remember at the beginning, we have our freedom to choose A. So now we just proved that already between VI, VJ, VK, the three clusters, the number of triangles is strictly bigger than AN cubed to get a contradiction. This is the contradiction. Okay, finishing the proof. In the remaining time, I will give a preview of what we're going to prove next time on Thursday. So wait, Thursday, we might have to change the lecture time also. Okay, on Thursday, we will see this application of removal lemma on a very famous theorem called 6-3 theorem. So here are some basic definitions we need. Let me introduce these basic definitions here. This big three theorem provides alternative proof for Ross theorem on three-term arithmetic progression on 3AP. Okay, so what is this 6-3 theorem? This is basically a Turan type theorem for hypergraph. Okay, so now let's work with three uniform hypergraph. That means every edge, remember, that means every hyper edge has three vertices, has size 3. So three-uniform hypergraph is you have a vertex set and you have an edge set, where this edge set is a subset of triples of vertices. Now a definition is we say a hypergraph is linear if every two hyperedge intersect at most one vertex. Here's example. This hypergraph, 5 vertices, 2 edges, this is linear, whereas this is not linear. This hypergraph, 4 vertices, 2 edges, the 2 edges share 2 vertices in common, right? So this is linear, and we call for ST being natural number, and ST configuration, configuration is a hypergraph an ST configuration in the hypergraph is a set of S vertices inducing at least T edges, hyperedges. And we say a hypergraph is XT free if it does not contain any ST configuration. Okay, so for example, this guy is a 5-2 configuration. This guy is a 4-2 configuration. Okay. And 6-3 theorem is saying if we forbid 6-3 configuration, then the graph cannot have too many edges. For any 3 uniform hypergraph H, 6-3 free implies the number of edges in H it's subquadratic. It's very sparse. Remember, a positive edge density in three-dimensional hypergraph is n cubed. So not only we have subcubed, we have subquadratic, middle of n squared. We're going to see a proof of this and an application of 6-3 theorem next time. Any question? Okay, if there's no question, I'll see you guys next time.